Thank you, Cyril. So in some sense, this last lecture is the one where maybe, hopefully, you will see things coming together. The first lecture was more, recalling, the global vision that had been outlined by Scott, and then in the paper by Scott and Bertrand on basically how quantum gravity should be understood when you use the Liouville area measure, and the relation with the conjectural relation with the limits of embedded planar maps. Then yesterday I tried to explain you a little bit about, mostly about CLEs themselves and how you could explore them and how they were, natural ways to, and why it was natural to look for these conformal invariant exploration processes of these conformal loop ensembles. And at the end I stated, one result where basically how these Markovian conformal exploration of CLEs, if you print them on top of a independently chosen Liouville quantum gravity surface, the exploration gives rise to Poisson point processes of random surfaces. So in some sense, it's one of these, the global theme in all these random geometry type things is that. Or the approach, related to exploration, peeling, SLE, or trees, all these type of approaches. Always say you have a two-dimensional mess in front of you, and things are correlated. Not so trivial. So how are you going to describe it? And well, if you want to use our usual tools of stochastic calculus idea or probability, martingales, whatever. You need to introduce some sort of time. You need to order the randomness by discovering it in a certain way. In the planar maps way, it would be, there are these natural bijections, and the goal then at the end, you have a bijection where you have trees, and when you have trees, then you have a natural, way to go along the trees and discover things. And then at the end of the day, end up with, nice one-dimensional structure where some independence and, Poisson-type processes show up. Right, so that's somehow the SLE thing is also a one-dimensional way with a one-dimensional Markov-Proust, a one-dimensional Brownian motion that is behind the scene that explores in a nice way and describes in a nice way what you have in front of you. Right. So, let me just recall the state. So here somehow the idea is that really the way you want to think about it is it's very natural, and we'll come back to that later. If you have a CLE and you have an LQG, if you put them together, right, they're independent, but then you put them together, so it looks more complicated, but if you can sort of discover them together along the, then you get something nice with Poisson point processes and things like that. So, okay, so and of course, that's somehow was already more or less, present in the initial, quantum zipper ideas by Scott. Except that here, when you explore the whole CLE structure, what you get is that you will, in the end, be able to describe, it's going to be one way to describe the whole structure that you have in front of you, and discover the whole structure, and then have the sort of natural bijection between these two approaches. Anyway, so let me. Just recall you sort of rephrasing of the result of yesterday statement, because I didn't say anything about the proofs, and I hope I'll have some time today, is that, you take this gamma quantum half plane, okay, and then you choose the gamma quantum half plane. So here gamma will be always in 1/3 full for what I'm going to say now. So it doesn't include, square root of 1/3 square root of 4. So it doesn't include the the smaller values of gamma that are below square root of 8/3, because for them there's no CLE available. At least there's none of these simple CLEs available. You can go all the way down for the other part when you take the CLE kappa prime versus story that I'm not going to tell you about now. But anyway. Okay, so you take a typical point. You have a CLE in front of you. That is independent of the surface, and you explore it in this Markovian way. Following the trunk. And when you meet a loop, you leave the loop to the right. The trunk is going to bounce on itself. It's going to bounce on loops, and the loops are always left to the right. I just should already mention that there's a version of the result when one can decide for each loop whether it's going to be left to the right or left to the left by sampling a different coin. And basically, when you hit a loop, you discover it all at once, right? I told you the trunk is going to be an SLE kappa prime type curve, right? So these are SLE kappa type loops. And this trunk turns out to be an SLE kappa prime type curve. It's sort of if you look at it, quenched way. And so one natural thing to look at, and this is a picture that you have seen last week already in, I think it was probably Gregory's lecture, which is at a time t, you have discovered what you know is that you have discovered some stuff like that. That's the boundary of the domain you have discovered already, so I'm simplifying things. Okay, so when you discover the loops, you have all your double points. So this is how things like. This is where you started, right? So here you have the trunk and the loops that you have discovered, and that's the whole of everything that you have discovered at this time. And clearly, I told you this, you can make sense of the boundary length here by definition of boundary length of the quantum length of the, boundary here, here and here. And here these boundaries are going to be SLE kappa type curves because they are, made out, the loops that you have discovered and the outer boundaries of the trunk. And so you can make sense of the, quantum length of this. Okay, this is where you are currently exploring, right, where the trunk is. Okay, this is the left boundary of the trunk, and then here you have these loops on the right. And then here on the left, you have the left boundary length, quantum boundary length, okay? And so here, the natural thing you want to look at is RT, right, is going to be basically the fluctuation of the boundary length to your right compared to how you started with. So basically, let's decide that this length is, say, little RT minus, and this length here is RT plus, and this would be RT plus minus RT minus. Okay, it's the fluctuation of the right boundary length. And similarly, you can define LT, which is LT, plus minus LT minus, which is the fluctuation of the left boundary length. Okay, this is exactly what we have seen in Gregory's lecture. And so the statement here is that, so let us just, look closely. Imagine that here at that time I discover a loop, CLE loop. So now suddenly, you're exploring here. So what you are doing is that this becomes part of your right boundary, and the discovery of the loop will make a positive jumps to RT. Now, if at this time the trunk hits the left side, right, then some green piece disappears. You have a negative jumps of L, okay, and of capital L, and if you hit yourself on the right, then you have a negative jump of capital R. Okay, so the moments where the trunk is sort of hitting your past correspond to negative jumps either of R or L, And okay, and the positive jumps, I mean the discovery of loops will correspond to positive jumps of R, right? So discovery of loops plus jumps of R, and trunk hitting past negative jumps of R or L. Okay, and one way to state the theorem is just to say, well, you know, RT, if you choose the right time parameterization, there are two independent for kappa stable processes. Okay, for kappa. Okay, that's one thing. So I should emphasize one, you know, something important, which is that these stable processes, they, if you look at their index, kappa is smaller than, you know, it's between. Okay, these are, you know, processes that are not just made by the jumps, right? These are, you know, the forward kappa is larger than 1. Okay, so these are the stable processes where it's not just made of the jump. You need to, you know, compensate, you know, the total sum of all the jumps will be infinite. You need to do some, you know, Liouville compensation near the origin. So in particular, the process, if you look at the process, so RT, oh sorry, LT has no negative jump, has no positive jump. Right? It's only, so I guess Cyril would have said it's spectrally negative. And RT has plus and minus jumps, and the ratio between rate of plus jumps divided by minus jumps is going to be equal to, well, this minus cosine 4 pi over kappa divided by 1/2. Okay, and the rate, you have to compare, you know, I just said, you know, this has only positive jumps, no positive jump, this has only negative, this has, so in order to describe the law for the two independent things that run at the same time, you have to say what the ratio between the negative jumps of R and the negative jumps of L are, right? And rate of minus jumps of R is equal to rate of minus jumps of L. Okay? So that just describes you this sort of boundary length exploration, which is exactly the type of thing that come up in the scaling limit of planar maps all the time. And then the additional thing is conditionally on these length jumps, the quantum surfaces discovered or cut off at the time of a jump of size L or H are quantum disks, independent quantum disks with boundary length H, right? So you can describe basically, you know, this is just going to, this process is going to tell you, okay, now I add a bubble of boundary length this, now I cut off a surface of boundary length that, right? And what is inside these surfaces, you know, you discover the boundary length, and what is inside here, you know, oh, this corresponds to positive jumps. What's the law of what I discover in there? It's just a quantum disk with that boundary length corresponding to that jump. So note two things. This is a quantum disk. It has just the only constraint is that the point at which you add, you know, the point at which you bump into your quantum disk has to be a typical boundary point, you know, typical boundary point of that disk, right? So it's a disk where this point is actually a typical boundary point. Okay, is that clear? So I just want to make one little comment, because it's going to come back you know, to haunt us a bit later, is that, you know, imagine that I start here. What are the points at which, you know, the trunk hits the positive real line? The point at which the trunk hits the positive real line, if you think about it, they are just the point at which RT hits is running minimum. Okay, you know, if R hits is running minimum, then you know that you are hitting the right-hand side of the boundary, so that the trunk is hitting the boundary of your initial domain. So this is also, you know, probably everything here is very familiar to everyone in planar maps. Of course, on the other hand, you know, I should emphasize that all these things, we don't do anything about planar maps, right? Sort of, it's just a natural thing you would expect from the planar map story, but we don't work at all with planar maps. It all comes from the GFF SLE story. Okay, so that's that statement. And now, as I said yesterday, I want to describe, we want, of course, you know, when I cut out this disk, or maybe when the trunk hits here and you cut out this other disk, which corresponds to the disks that you discover when you have a negative jump. Well, you know, the goal here is to describe the whole quantum surface that you have in front of you by discovering it entirely. So here you start with a half plane, you start discovering, and then you have a bunch of disks. But even if you would be interested, say, in the scaling limit of you know, Boltzmann maps, decorated Boltzmann maps, or, you know, the Boltzmann maps themselves with large faces that correspond to the thing where this would be a large face of your planar map, but here this is not a large face of your planar map. This one, you still have to continue exploring there, so you need to basically be able to continue exploring inside a quantum disk. And if you're looking at the models where the ON type, Bourreau-Boutier-Guiter type things, you might want to explore again inside of these disks, because inside of an ON loop you have, again, you know, nested versions, and you can sort of continue exploring that. So it's important, somehow crucial to be able to describe what happens if instead of exploring a half plane you explore a disk. And then the statement sort of you have a disk, okay? So we choose, this is a gamma quantum disk, and this is a boundary typical point, right? And imagine that this disk has a boundary length, remember, I call delta, okay? And we are going to decide to explore it, right? We put a CLE, independent CLE kappa on top of it, and we explore it in exactly the same way. Right? We do some exploration. For instance, we can decide to target this point, or we could decide later, you know, each time one has to choose whether to go to the right or to the left, one can decide to go to the right or go to the left, and now we're going to again have something that are basically essentially the continuous analog of things that Timothy has been explaining. So here, what is the difference? Well, the first remark I told you, this is basically what you see, the quantum half plane is what you see when you sort of locally zoom in near the boundary typical point of a quantum disk. It's sort of, right, sort of the evolution of what you see here at the beginning will be absolutely continuous, you know, until you're not going to be very far to the evolution of what you're going to see there. And so, as you would expect, sort of the description of what you see here, you know, there's probably a way to say that it's the same as what you have there, except that, you know, the Gaussian free field has changed. There's a nice Radon-Nikodym derivative, you know, between the law of the Gaussian free field near the boundary typical point of a quantum disk and near the boundary typical point of the half plane. And once you have that, then, you know, probably the thing you're discovering, you know, if life is nice, the thing you're discovering here will be a natural H transform of, you know, the thing you have been doing in the upper half plane. And the answer is basically the discovery process here is a simple H transform type modification of the previous one. And maybe I'm going to just, describe it in this, the most, it's not super formal, but it's sort of, I think, more probably the simplest way to understand what is going on. Basically now, if I explore locally, I haven't told you yet, how I'm going to do my choices to when I cut out, when I have the choice to explore to the right or to the left, when I want to, when I'm going to explore the thing here. But the basic thing is the following. The idea is sort of moral, is that the partition function of the quantum disk, or sort of maybe the energy, energy of the quantum disk of length L, will be something, the power of L. And so what I mean here is the following, is that when you discover, does the exploration, right? Then you start with a disk of boundary length delta, and then what can happen? So this is a disk with boundary length delta. So you might discover a loop, okay? A loop now with boundary length h. So what you end up here now are two objects which are independent disks. A disk with boundary length h, which is the one inside, and a disk with boundary length delta plus h. That's the idea. That's what you want. Okay, because you want that what you still have to explore in all directions are disks. Okay, so this will be split in delta plus h. So now there are two disks, one with delta plus h and one with h. And in the case where where the trunk hits, the thing where the trunk hits the boundary, that corresponds exactly where the point where your previous, where you are exploring this, your trunk almost hits the boundary, so the picture just before was like that, and just after that you have cut this out, and now you have boundary length h here, and this would be now delta minus h. Okay, a pair like that. And of course the delta minus h, and the delta plus h. So here in that case it's pretty clear how you can order them, because you take the largest one first, and and here in that case, of course, it's not so clear which one you put right first, because I haven't told you who's on the right, who's on the left. So either you decide to put the one on the left first, or the one on the right first, or you put the largest one first and the second largest one here between these two values. And so maybe you can put something like that, delta over 2, just to make sure that you know what we mean. Okay. And now I told you here these are the jumps here are independent forward capital stable processes. So that if we were in the case when capital delta is infinite, which corresponds to the half plane, the jump intensity of jumps here would be, that's, if there would be no delta, the local intensity of jumps through here would be just dh over h to the alpha plus 1, and here dh over h to the alpha plus 1, indicate with this minus cosinus 4 pi over kappa term. Right? This is the intensity that we would have had, that would come from this type of consideration. But now we are in a disk, we're not in the half plane. And so the idea, so what is going to be the natural H transform? You know, if you think about that, somehow the partition function will have just be to be the boundary length to the power H plus 1. You know, what's the, you start with delta, so then you put a delta to the alpha plus 1. That's the, you know, somehow the energy that you had at the beginning, and the energy you had at the end now is delta minus H. Okay? That's your transform. So this is just the description of this growth fragmentation process that you see when you have your discovery of a quantum disk. Okay? So it's pretty clear that this is sort of the infinitesimal generator of your stuff, you know, and you have this branching structure. You know, once you have branched, then you can decide to explore this one or this one, and you'll do that independently. Here's the same. Okay? Does that make sense? Right? So when capital delta goes to infinity, then this would correspond exactly to basically, you know, the positive jumps of L, right? And on the other side, you add the positive and negative jumps of, I mean, the negative jumps of L and the negative jumps of R, you add them together. So in some sense, this you know, the evolution of this boundary length corresponds to evolution of R plus L, if you want, on the other side. Right? Because I haven't told you what is on the right and what is on the left. Okay, is that clear? Sort of the description. So now, once you have this, you know, then you can make your choices. If you want a one-dimensional process, for instance, then you can decide. You know, your rule would be to say, well, I'm always following, say, the place with the largest boundary length. Right, so that would be a nice Liouville process where you jump from delta to delta plus H with that intensity, and you jump from delta to delta minus H with that intensity. Right? That's just trying to navigate, always exploring the face with the largest boundary length. Okay, that would give you rise to a nice, you know, one-dimensional Markov process with jumps that locally is absolutely continuous with respect to this asymmetric stable, right, where the ratio between the positive and negative jumps is given by this magic number minus cosine 4 pi over kappa. Right, the 1/2 disappears because you have the negative jumps of R have been added to the negative jumps of L, and therefore we have 1/2 plus 1/2. Okay, is that clear? So you see that here. This gives you the full description of the whole, you know, the recipe of how to discover your CLE disk, the quantum disks, you know, on which you traced a CLE quantum CLE, by just saying, well, that's the you know, Liouville type process rule that you have to follow. Okay. So of course, you know, the time at which there's the question about what is the time that is between, you know, behind the scenes here. So of course, there's a slight subtlety. So, but you know, for instance, if you would have time changed everything by removing this intensity of jumps, you would have just time changed the entire discovery. I find it more natural to add this delta to the alpha plus 1, but it's not necessarily, you know, okay. Okay. So this time that is behind the scene here, let's put it here, is somehow the natural, you know, quantum time parameterization of the trunk, right? It's sort of the natural quantum length, if you want, of this green curve that we have there. I don't want to say too much. Okay, so I hope now you have a sort of right. So here we see the idea is, and then of course, you know, once you know that, and again, conditionally on the jumps, the law of the to be explored surfaces are independent quantum disks. Right? So what I have in mind is, you start at delta. Somehow you have your your gross fragmentation process. It's like a tree-like structure. You can decide, for instance, always to explore the one with all the jumps following the one with the largest, right? But here, maybe at some point you say, oh, here I have there's another one that looks pretty nice. I can continue to explore it. So you can. It's like this continuous stable tree of decision makings that you're exploring. You can explore a finite piece up to here, up to here, up to here, up to here. So now you know that here you have leaves with hanging around with all boundary lengths of two of structures that you haven't yet explored. And the idea is that conditionally on this tree, all the remaining to be explored things here are just independent quantum disks with boundary length given by the label that is sitting there, the boundary length there. All right. So, and of course here you see that there is this. Okay. Is that clear now? Okay. So, for instance, one thing you could do is, you could start from there and decide also to continue exploring inside each of those ones, right? The disks that were actually loops. If you think about this as this ON type model, you can again continue exploring another CLE embedded in there. And so there are things you could try to do, which is, for instance, start with this. What this gives you is you can start from there, and you continue exploring all the branches and you stop at first time if you see a quantum disk of boundary length smaller than epsilon, you stop, right? So this way you decompose your thing, okay, and you will end up just with bunch of very small quantum disks, and somehow the whole structure is reconstructed as gluing of these all these many small quantum disks of size epsilon, and of course you would sort of feel that in the limit, when epsilon goes to 0, these small quantum disks, they would correspond to just something like small little faces of your model somehow, right, in the planar map world. Okay, just to okay, so now I want to make a few comments. A consequence of this thing is that it's very natural, once you have this description, to define the natural LQG measure supported in the CLE carpet. Okay, right, so if you want to think of term of planar maps, you take the planar maps with large faces, so that means that once you see a loop, it's a big loop, it's just a large face, there's nothing in there, and then you try to look at what is the limit of the counting appropriate your rescaled limit of the counting measure on your planar maps with large faces. And if the life is nice and good for us, this would give, would be a natural measure that you could define directly in the continuum as just being, you superimpose gamma LQG and an independent CLE, and you just look at the trace of the gamma LQG in this fractal carpet of dimension 0, of positive dimension, but Lebesgue measure 0, and there should be a natural, there should be a natural measure sitting there. And here it's pretty clear how to do it, right? I mean that there are 2 or 3 different recipes that you can try to follow. One would be to say, well, there are natural martingales, and when you follow the exploration, so there's if you want your measure to have some sort of scale invariance property type scaling property, then there's just one choice. Another way would be to say that if you do something a bit like here, something like for instance, one characterization would be mu of O, or nu of O, right? Which would be sort of the limit when epsilon goes to 0 of, I think, epsilon to the alpha minus 1/2 times number of loops of length greater than epsilon in something like that. So, right, so basically what you're looking at, so of quantum length, right? So what you have here, I have a set O. I cut out all the interior of the loops of these loops here, and somehow the natural measure, quantum measure that sits in the carpet, right, could be viewed as looking at you count how many when epsilon goes to 0. Of course, you have these loops that correspond to that each of them has a different boundary length, and you just say, well, I count how many of them there are that have a length larger than epsilon. This is going to blow up when epsilon goes to 0, but it will blow up in a way that is sort of uniformly spread according to this natural measure you want to look at in O, and that would be one recipe to get that. Okay. So in some sense, you can make sense of what it means to choose a point at random, right, according to this measure here in the embedding there. So in some sense, it would be the analog of if their embedding is nice, and if we believe in the global LQG, quantum gravity embedding story, that would be the limit of, a typical point in a planar map with large faces. Okay. But here, and then you can do all sorts of other, computations that are based on this, this branching procedure. Any functional that has nice scaling property would give, and of course, these type of, branching splitting processes are exactly the same that appear if you start with a nice planar map structure for which you have all sorts of very nice, combinatorial properties such that enable you to trace, to track in a sort of Markovian way the exploration, the peel that, are amenable to peeling processes where you have a nice Markovian structure there. You will end up, with exactly the same, explicit formulas for the discrete things. You saw in Gregor's lectures, if something is domain of attraction of a stable, blah, 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 then in the end you have a stable process. Okay? And then the stable process will correspond to exactly these things. So then the computation that you make using the two same stable processes give rise to the two same formulas, right? So then, once you have the branching process, then you are happy because you can say, oh well, Lévy and Bertoin and there are all these magic formulas that you have about the growth fragmentation process, and some are nice, and you have explicit function things or not explicit. Okay, but somehow the key is just the description of the mechanism. Okay, so now I want to make a few more comments. So one comment I think which is important here, which probably also is going to be related to what Nicolas might say. So here in some sense, what this exploration is doing is you're choosing a boundary typical point, and then you're sort of exploring from there. If you want to try to think about, distances, we have these things that have to do with the area measure, scaling of the area measures, but of course in these peeling type processes, they are super cool because, you can relate them directly to the metric. They tell you something about the distance to the root, and, you can read things about the metrics. And here, of course, on the LQG side, we have nothing with metrics. So I just want to just mention one thing, which is in some sense maybe one has to be a bit careful, which has to do with the fact that this exploration mechanism was quite subtle, because in the there was some randomness here in the exploration mechanism. So for instance, the time, if you look at this picture, the time at which I'm going to discover this loop right? Because of the result we had in with Scott and Jason that told you that the time at which you're going to discover this loop when kappa is strictly smaller than 4 is actually, that the trunk is not a deterministic function of the carpet. This time is going to be random. Okay, so you're not going to be able to say that, well, the distance between this loop and this root is just the time, at which you discover it, because you have added some extra random information that is sort of coming from the microscopic world. So somehow that there is some information in the time at which you discover the thing that is dependent on choices that are things that you don't see in the stable process, right? So there might, that there is some randomness that has been washed away by the stable process, but that is still existing in this discovery procedure. That has to do with doing the percolation within this fractal carpet. So, for instance, one very natural, variant of the discovery process that you want to introduce, because one of the ideas that you have is that, if I start exploring if you think about it, this description here tells you that if I stop my process at the typical time for this Poisson point process, I start exploring. So what you have in front of you, the discovery of what you have in front of you is just follows the same rule with the same jump things. So therefore it's going to be a quantum disk as well, right? So what if I stop at any natural time here, my exploration, what I have in front of me, the remaining to be discovered domain here, is going to be a quantum disk with size, boundary length given by the delta that I have in front of me. And this point is just a boundary typical point of that quantum disk. So one very natural thing to do would be to say, well, why do we decide to continue choosing exploring from there? We could decide to say, well, let's, make a jump and choose another exploration point uniformly chosen along the boundary, such that, and now we start exploring from there. Okay? Or you could say, well, and you could make these jumps at every, delta piece of time, and then you could let delta go to 0. And of course, the boundary length, this description of the boundary length of the remaining to be explored domain will not be affected at all whether you explore from here or there. It's just the boundary length of, your splitting mechanism. So the same stable processes mechanism, right, would describe as well this sort of process of QLE type that you would get here that would correspond to, instead of growing locally always near the tip of, a Markov exploration, you sort of each time a jumps come in, it comes in from a point that is uniformly chosen on the boundary of the disk that you're currently exploring. So then now you have something which is very natural in this coupling procedure, where you sort of grow from everywhere at once in the natural way defined there. And then of course this is like, this is the spirit of the QLE growth mechanism, where you are just growing everywhere simultaneously with an intensity that has to do with the quantum boundary length of what you have here. But of course here, the big difference here is that the exploration mechanism here was independent of the LQG. It was just depending on the CLE, and it was a nice, curve. And here you have this jump thing, and of course the way the speed of the exploration at different points, the way this is going to grow will depend, will be coupled, depend on the LQG thing. Okay. On the other hand, this one is sort of, if you want to think of distances, scaling of distances in the dual graph, right? So where now it's distances between faces, okay? So then you are going to say that all these points that are inside one of the loops, of the big loops, they're contracted to one single point. So then when you try to explore, from everywhere at once, then you are doing something that is reminiscent of first passage percolation, in the other thing. So this type of process that I've described there, when you discover from everywhere, they will be naturally related to things that are quite natural on the planar map story as well, and that will be probably also relevant for distances and things like that. So the same. So what I want to say is that if you see in the discrete world something that is actually given rise to that, it doesn't mean that it corresponds exactly to this exploration, right? Because what you could have done is, instead of exploring here by doing percolation, you do another way to think about it. By exploring, instead of doing percolation, you explore by doing something like subcritical percolation. You always go more to the right. Right? So this is basically saying, in the planar maps world, you have this thing here, this edge here. Either you discover this is a big jump to negative jump. You explore to the other side, it's a big negative jump on the other side, or you discover a big face. Okay. And the question here is somehow, when you discover, something small like that, where you go, which is the next edge you're going to go at. So if you are not very careful about, how this corresponds to the actual percolation in the eventual face, then you might have a drift, and you might, go like crazy to the right. And so that means that here on this thing, you're just, going to turn around like crazy if you trace the image in the natural embedding like that. And then at some point you find, I find a new face, and then you discover a bubble. But because you did, go like crazy around it, according to the boundary length, if you turn infinitely at random and then you stop at some random time, it's exactly the same as choosing a point at random on the boundary. Okay? So, it could be that when you take the scaling limit of something which, is not exactly balanced, you get exactly this process here. But you actually get this growth mechanism, if you embed it, then you will get rather this one than the one where you can actually follow the continuous trajectory. Okay, that was just one warning. So now I want to say a few words about some of the ideas, because of the proofs, but still I felt was more useful to try to convey the nature of the results and why they are relevant, and why this is going to, if you think about it, I'm not going to write the little diagram here, but you have what this sort of type of structure tells you is that you have, once you look at the the results, the great results that you can get, explicit results that you get by scaling limit of discrete maps, planar maps decorated, or large faces, or something that are amenable to computation, then the coding by trees and something goes exactly to the coding of the continuous structure, right? And so that gives you, then at the end of the day, you will get some convergence to the continuous object that has the same, structure there, and in some sort of topology, right? It doesn't tell you what the embedding is, but it just tells you the coding things are the same, and something reminiscent of pianosphere type topology, right? So the encoding, both things are encoded. There's a bijection between the encoding here and the object here, the encoding here and the object there, and the encoding converge. But still, it's also this relation with LQG. If those of you who saw the square root of 8/3 things by Scott and Jason and so on, it gives some feeling. There's some hope that one can maybe even get better things there. But I don't know. I'm not claiming anything. The other thing is, if I have this discrete tree that is very close to the planar map, has an encoding thing that is very close to the continuous one. The continuous one is naturally embedded by the thing that you have there. So then you can try to use some sort of, it tells you that maybe there's a coupling, there exists a coupling, so maybe it gives you some existence of possible embedding such that this and that. Nothing explicit. Okay, that's just the global idea. Now I want to, what did I want to say? Yeah, so there's one thing I want to explain, which is like, how do we get pop-up? In the discrete world, from the planar maps, there is, the relation between the gamma and the ON. So you have the explicit ON, you have the explicit, jump procedures, and you have, the constant, the ratio between the positive and negative jumps comes out, naturally from the discrete combinatorics. Now here, where does this come from? And this is a highly, from the continuous side, that's a hard nut. Somehow, it turns out. It's not something that you get, out of, for free. And the way we do it is probably maybe not the optimal one, but it's the only one we can think of, right? And so the idea is the following. So the idea is, well, we look at the dimension of the set of points at which the trunk intersects a loop, right? So remember, we're discovering this thing here. I have a loop, and then there's this trunk decomposition. The trunk hits the loop, and then it hits this loop again, and then it goes like that. So in the Euclidean world, okay, this is something you can compute, because we know this is locally, the green thing is SLE kappa prime type thing. The outer boundary of an SLE kappa prime type thing is SLE kappa curve. So locally it's looked like an SLE kappa curve. And we know by the, the CLE percolation story, we know the law of, this loop conditionally on the green one, and we know locally this will be like an SLE kappa rho type curve with an explicit rho that we know. Okay? So this is an intersection of an SLE kappa type curve with an SLE kappa rho type thing defined in the complement of it. This is not a trivial thing to look at, but there's a paper by Jason and Howe. They computed this fractal dimension here. So we know what the fractal dimension of these points are in the Euclidean world. Now the exploration is independent of the LQG, and so you can apply the KPZ formula, and this tells you know what the dimension of this set of points is in the quantum world. Right? There's an explicit formula for that. Now on the other hand, when you look at the encoding, I told you the times, you can look at it the other way. If I this set of points, they correspond to, I first discover the loop in the exploration, and then the trunk is going to bounce on the loop when you explore it. So at the time when you discover the loop, then this is part of the boundary. Okay? And so these intersection points are exactly the same story as when I start here and I do that in the, when you apply the conformal transformation. So this quantum dimension of points on the SLE curve will be exactly something that is described by the times at which this stable process with positive and negative jumps, because you're looking at the one to the right, is at its running minimum. In terms of dimension, that's how you're going to describe it. Okay? And here, there are, you open Bertoin's book and you say, well, okay, the dimension of times at which, an alpha stable process hits its running minimum. There's a very nice formula, that gives you the dimension, that relates this dimension of times to, the ratio between positive and negative jumps of this alpha stable process. And this is a formula that involves something with ratios of sinuses of pi times the dimension, something like that. So one of these nice magic formulas that you can have in these alpha stable processes. Okay, and then, so there's the, then Bertoin type book about, the dimensions. And then there's this almost sure KPZ formula for subsets of SLE curves by, again, so Ewain, Miller, Jason, and Nina, that tell you, roughly speaking, that if you know what the dimension of this subset of times is for the natural parameterization of the SLE curve, then you see how it transforms the dimension in terms of, what you could say, what would be the natural dimension that corresponds to what you get up there. Okay? So this says that you have, and then you have to say, well, but these two dimensions have to match. This one is a function, this one we know, and this is a function of the ratio between the positive and negative jumps. And therefore we know what this ratio is, and it turns out that you do this. It's a big formula, blah, 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 everything cancels out. At the end, you have minus cosine 4 pi over kappa. All right? So, that's just a... Now, I want to emphasize another thing, which is that the result I stated here, this is just a very particular case. This exploration of an SLE of a half plane or a quantum disk by the CLE kappa exploration structure is one particular thing. So there are a number of variants. So one variant would be explore something else than the CLE, right? So something that would have to do with the SLE kappa rho kappa minus 6 minus rho type exploration processes. That would be BCLE exploration of BCLE structures in your domain. That would be one way to think about it. So that there would be one thing that you can explore other things than maybe other structures than disks. Maybe you will get wedges and other variants that will be naturally coupled to whatever you want to explore. But I want to there's one very important generalization that has to do with kappa prime when kappa prime is larger than 4. So now the idea is you're going to, instead of exploring an CLE kappa, you're exploring a CLE kappa prime. So which means that, for instance, you're exploring the clusters of the FK percolation model that is sitting in front of you rather than the clusters of the Ising model. And so if you do that, then basically everything, the statements are exactly the same. All the formulas are exactly the same. The splitting formulas are exactly the same. You're always exploring a gamma Liouville quantum gravity surface where the gamma is the square root of kappa, where kappa is 16 over kappa prime. So because there's a natural duality between, so it should not surprise us because there's a natural duality between the CLE kappa and CLE kappa prime that comes from the CLE percolation story or FK Potts type duality. And so, but then, there's something, very different that has to do with the fact that, as people, know, the surfaces, the disks that you're exploring, or the quantum surfaces are exploring, there will be like the trace of what a Gaussian free field looks like, of a whole plane Gaussian free field looks like inside a SLE kappa prime type loops, which has these, cut points everywhere. So then you get these loop tree type structures and I find it a helpful way to understand in retrospect also to revisit a lot of the mating of trees things and forested trees and these structures that are appearing in Bertrand, Jason and Scott's mating of trees paper because it's sort of just very similar to that story. I'll try to come back to the relation with the mating of tree papers a bit later. Now, so one important thing is one natural extension, and that's nice because in some sense, I think it's fair to say that wasn't our, maybe, we with Scott and Jason, we're maybe like SLE kappa rho geeks for rho smaller than -2 and how cool these processes are, and they're totally crazy. They're doing these, the trunk is not a deterministic function of the jumps and all these type of weird things. And there's something natural that you can do is like, imagine now that you have a parameter beta. And this is a purely CLE thing. You have the CLE in front of you, and you color each CLE loop, will be white or black with probability 1 plus beta over 2 or 1 minus beta over 2, right? So some of them, and this you could view that as they get an orientation depending with parameter 1 plus beta over 2 or 1 minus beta over 2. And this basically independently. And this should be thought of when you meet this loop. Are you going to leave it to the right? Are you going to leave it to the left when you explore it? So in some sense, if you think of percolation in the complement, are these holes or are these things contracted to a single point? And now what we showed is that there's this natural trunk, right, that correspond to, this idea that, some loops are left to, when you discover a new loop, it will be on the left or on the right with a certain probability. And then there's a unique way to make sense of what can be called as the critical percolation in this domain, interface in this domain that is sitting in there. And what we had is that we knew out of abstract characterization of this process that this trunk was a process that is explicitly described like that. So trunk right? This is a process like that. I don't need to explain to you this, but it's one of those type of processes. There's sort of target invariance property and so on. But the way we get the proof was there exists rho such that it's equal to one of that. Right? So there's this thing, you have this Poisson point processes of bubbles, some of them are positive or negative, it's exactly like you get the jumps of your Liouville process and then you construct the Liouville process, then you get the stable Liouville process, then you get the whole, you get the curve, and this curve has a nice decomposition between trunk and loops. And the law of the trunk itself, the quenched law of the trunk, is just one of these processes, but we didn't know how to identify the value of rho. We had no clue. Right? So from the purely CLE, SLE world, we didn't know how to do that. Now with this trick, one is able, if you go around, we do the same analysis as we did for the, beta equal 1 would be just the one we just saw before. And now the idea is just to say, well, if I do this exploration mechanism here, well, you can guess what's going to happen with it's going to be exactly the same story as before, except now that some of the positive jumps will be on the right and some of the negative jumps will be on the left. And of course, what's the probability when I see a positive jumps that it's on the right? It will be 1 plus beta over 2, and that it's on the left will be 1 minus beta over 2. Right? So now you have 4 Liouville processes, you have 4 types of jumps, the negative jumps to the right, the positive jumps to the right, the negative jumps to the left, and the negative jumps to the left, positive jumps to the left. So you have these 4 types, and it's exactly, on the quantum world side, it's pretty clear. The ratio, you'll have intensity 1/2, and that minus cos 4 pi over kappa times 1 plus beta over 2, and 1 minus cos 4 pi over kappa times 1 minus beta over 2. Okay, and then you sort of apply some generalization. It's not, it's a bit more complicated than that, but this type of argument enables you to get the explicit formula for the value of rho here. Okay, so we know what this value of rho is, and I wrote it here just for the record. So you get something that the ratio between positive and negative jumps, which is something like that. I mean rho over 2 plus pi chi prime over 2. Okay. So, and that's a formula, it's just a formula about SLE, right? This has nothing to do with Liouville quantum gravity, it's just describing the law of the trunk of all these things. And we don't have it's one of those cases where this is a result, purely result about SLE, and the only way we know the answer of, we can prove it, is actually to make this big true. Of course, the experience and tells us, that eventually, probably, there might be a direct way to look at it, I don't know, and to avoid going to this gamma LQG detour here, but we can't really think of any, route to try to get there. So that's just an example of how, this quantum gravity thing, that's probably one case where, the quantum gravity approach beats all the other ones, right? That is just the only way to get this result here. Now,
even heuristically,
yeah, even heuristically. This formula, if you look at this formula, right, and if you think about these Bertoin running minimum formula, these are exactly this is exactly the way these formula for dimensions of, running dimension of running minimum look like. It's sinus something about sinus something plus something else, where that's just the way these. So this formula suggests, that's where it comes from, right? Sort of.
It was not only a technique to prove, but just also to find the formula.
Yeah. We had no way to guess what the formula was, and so the fact that the formula exists, we thought okay, it's some rho, but formula, why should there be a formula? And somehow, the reason why there has to be a formula is because, well, given, there is this decomposition and something, special happens there. Okay, so just to conclude, so what I talked about, in some sense, substantial part of the first lecture is, is there since, it's out there for many years, 10 years, sort of quantum zipper paper, the first paper by Bertrand and Scott, maybe Christophe's survey of their work in the Bourbaki seminar, Christophe Garban, there are all these things are there. Then the CLE stuff, there's, the construction of CLE, then there's the CLE, the CLE construction. I should emphasize that the CLE construction for kappa smaller than 4, you don't need imaginary geometry, you can do without it, but for kappa larger than 4, you need the reversibility of SLE kappa prime, which at present the only proof uses the imaginary geometry layer of papers. Then comes the CLE loop trunk decomposition, which is this long CLE percolation paper. So, each of these papers I'm mentioning are, probably more than 80 pages or something like that. But that's sort of the okay. You have the CLE percolation type thing that also builds quite heavily on some tricks from imaginary geometry. Okay, and then just the coupling. As soon as you start doing the coupling with the LQG world, then you have these layer of, you have the quantum zipper paper that was already there. You have the various papers in the square root of a third. I mean, many nice, great, long, and rewarding papers by Jason, Scott, and co-authors. And so what I describe here is sort of 2 papers in progress that will be called, a CLE on simple CLEs on Liouville quantum gravity that will correspond to kappa smaller than 4 case, and the other ones which correspond to kappa larger than 4 case, which are sort of going to describe this world. Okay, I'm out of time, so I'm not going to be able to make more comments, but I hope I convinced you that there is some interesting things to be learned there. And also, I think this approach is also gives a nice way to also maybe tie direct contacts with some of yeah, okay, I forgot to say that, the whole LQG quantum gravity things has another pillar which is built on the Rode Vargas, Kahan, Liouville world there. So I think, the CLE version FK, random covering of FK, and gives rise to understanding the, once you have the natural measure here, you understand things that are having to do with, correlation functions between what happens here and there. If you then apply, different coloring of FK clusters, I mean, here what you get is, in the kappa prime case, you get the scaling limit of the measure on the FK clusters, and then if you start to, want to look for partition functions, then you are, conditioning your points to be in the FK clusters, so you have to renormalize in a certain way, and then you get the, the random colorings type. So, and I would suspect that, these size bias thing, by conditioning them, these various points to be in various clusters would should be directly related to some of the DOZZ and Bouchot type formulas that one gets. So it's just not a way to prove them, but it's just a way to interpret them. Let's put it this way, or to tie, direct links between these various pillars of the same, people wanted to investigate these random 2-dimensional structures, and at somewhere, what happens on the various sides should be able to talk to each other. So I didn't have time to discuss that, but maybe Guillaume will say some words about it, or Ewain, or what is going on there. Okay, thank you very much.
Okay, we have a few minutes for brief questions.
There might be an alternative way to find this cos pi for the kappa, blah, blah, blah. Once you know that there is a gross fragmentation process, in the work with Tim, Bertoin, and Igor, we identified there is a one parameter family of gross fragmentation, such that if you look, say, at the fragment that goes towards the distinguish point, you see a levy. You see a levy, stable levy.
Yes, yes.
Say condition to die at 0. And there is a one parameter.
Yes, yes.
So if you know that it's a stable levy guy, automatically.
I agree. I agree that the somehow to use the KPZ formula, but still, you have to first, you get to the stable world, and then once you're in the stable world, you can get the computations. But so what you say is that it's true that somehow this formula here, this minus cos pi over alpha or alpha pi, that's a formula that if you open Bertoin's book, this minus cos pi alpha is there independently of any considerations. So yeah, that might be nice. Yeah, would be nice.
So is it true that the relation of this to the mating of trees paper is that you do the exploration, you cut out the loop trees, and then you can glue them back according to the mating of trees?
Okay, so I guess Jason, Scott, and Bertrand would be better, positioned to answer this. But you see, in the mating of trees paper, there are two. What you are doing, in some sense, is you are discovering along the SLE kappa prime type thing. You're not discovering the CLE loops. Okay. So in that case, what you have is morally that you are discovering your structure, and you're discovering your thing here, and it's sort of reminiscent to the decomposition I gave, except that you only have the jumps only go in one direction. You only have the negative jumps. You can only cut out things on both sides, and you don't have you don't insert the positive jumps. Okay. Other than that, it's as if there would be only. So, for instance, in the case kappa equals a third, which correspond to minus cos equals 0, which correspond to CLE being empty, then the loop trunk decomposition of the discovery. What's the natural discovery of the CLE a third is just SLE6. It's just doing the percolation, percolation thing in the plane. Okay, so in that case, the mating of trees is exactly the same as the just the discovery of the exploration process there. Now the other thing here is if you do here the thing when you there are a number of. It's both very similar, and both there are some slightly essential differences in the way that here you discover the whole kappa prime loops at once. Okay, so there are sort of. Okay, so I don't know if Scott or Jason want to comment on how to. They're politely smiling and don't know what they think. Yeah.
I imagine you can construct the LQG measure on the carpet directly with the
Yes.
field against the. Is there a direct construction of this?
You mean another one than this one?
Yeah.
Yes. Yeah. There are sort of various equivalent things. There's one very, very. Okay, maybe I should emphasize one point. That's a good point. Thing that is. The question is, if you use some constructions that are related to the exploration, say, using the martingales, then there's a question that says, is the measure one constructs there intrinsic? Or, you see, because you have this additional randomness that comes from the percolation thing in the trunk. And also, in the exploration thing that you have there, you have to choose the route. Right? So, the nice thing about this description, which is equivalent to the other description that we have, is that this one is intrinsic. It's just, LQG, and then you look at the length of the loops. You don't talk about the exploration at all. So that's what makes this sort of more natural. Yes, the other, just want to use this question to answer another question nearby, which says that, you know, one of the main problems on the map side, right, in order to understand the limit of the metrics, is that you start the exploration, you fix a route, and then you explore this thing, and you get some information about the distance from that route. Okay, so you have some sort of tightness procedures, tightness going on. But then the question is, you know, how do you correlate the exploration from here with the exploration from there? You know, how do you get the distance between any pair of points, not just the distances to the route? And that's, you know, one of the hard nuts to, you know, how to make sense of the limit. Show, I mean, even in the square root of a third case, to show the you know, to upgrade the convergent subsequential limits to existence of the limit, you have to be able to do some sort of resampling and exploring, you know, the trees from different points and say that the metrics are the same whether you start from there or you start from there. So of course here in the CLE world, you know, the CLE, you know, the exploration of the CLE, you can always explore the same CLE, right? You know what the conditional law of the exploration is given the CLE and given the Liouville quantum gravity thing. So this sort of, you know, root invariance of the structure we have is sort of maybe useful to, you know, say something on the other side, you know, about, you know, if you know the exploration here and the exploration from there, they are both very close to something which is the exploration of the same structure, right? So that might, you know, give some hint to how to try to get there. Yeah, sorry.
In one of your versions, simply the carpet measure,
yeah,
multiplied by the proper exponential of the GSF.
That's exactly.
Proper KPZ exponent.
Yes, yes. Of course, you know, if you want to look at the dimension of this thing here, you know, the scaling thing will give exactly the KPZ formula because you can see the, you know, so you know, this type of guy here will have to, you know, you will be able to relate it to just KPZ formula applied to the Euclidean dimension of the carpet. That's correct.
Okay, I propose a short break during which you can continue discussing with Wendelin, and we will resume at 25 for Alan's lecture. Thank you, Wendelin.
Thank you.